Welcome to Module 16, Part 3 of Modeling and Simulation. In this module, we will implement the wild dog model in NetLogo. Let's get ready. So here's the plan. First, we will define the breeds and their state variables. Then we will associate dogs with their collective. We need to solve the question how a dog knows which pack or disperser group it belongs to, and how packs and groups know which dogs are in them. For that purpose, we will create an undirected link between each dog and its pack with link neighbors. A dog can always use link neighbors to identify its collective, and the collective can always use link neighbors to identify its members. However, link neighbors will disappear if the dog dies. Next, we will define the global variables, and in the setup procedure, which you can see to the right, we will create each pack. As a pack is created, we will have each pack create its dogs and the link to its dogs. To keep track of which dogs are in which pack, the model will use an undirected link between each dog and its pack. In the Go procedure, we start by updating the dog's age with each tick and then the status. This happens with update pack alphas. Second, we program reproduction, dispersal, mortality of individuals and collectives, and pack formation. This is the heart of our program. Lastly, we need to ensure that all dogs are linked, either to a pack or a disperser group. And finally, we show our output. Of course, we need to build a dispersion submodel to account for how subordinate dogs decide whether to leave their pack and how they form a disperser group. You can already guess that this is not a submodel about the individual dogs, this is a submodel about the packs. We start by identifying the subordinates, and we will stop if there aren't any. In our dispersion submodel, we need to check for both females and males. And we handle the cases in which exactly one female or male exists in the pack. Those packs use the random Bernoulli function to disperse, and in which more than one female or male exists in the groups. Those are the groups that will automatically disperse. Now we need to program the dispersion. We do this with a generic procedure create disperser group from, which takes as its input an agent set of the dogs that disperse. We display the group. The authors have chosen the shape of a car here. Well, anyway, interestingly, the disperser group sets the variables of the dispersing dogs first by unlinking the pack, then creating a link with the disperser group myself, and finally displaying them on a radius from the disperser group. So let's now figure out what parameters are needed to run the model. The most important of these is the meeting rate. Let's say that our wildlife reserve management is trying to find ways of accelerating or slowing down the rate at which disperser groups meet and create new packs. They want to understand how important this meeting rate is and if it makes sense to, for example, build or remove fences. So let's do this. We represent the meeting rate as a parameter, here called disperser meeting rate, that represents the mean number of times per year any pair of groups meet each other. To investigate the importance of how easily dispersers meet each other, let's do a sensitivity experiment that varies the value of disperser meeting rate over a wide range. So the question is, how does management affect persistence of dog populations? We can look at this from two perspectives. How frequently does the dog population go extinct in 100-year simulations? Or how many times out of 500 replicate simulations there are no dogs alive after 100 years? As you can tell, we need to set up a behavior space. In our behavior space, we vary the value of disperser meeting rate over a range from, for example, 0.0 to 2.0. We can then set the stop condition for measuring runs to count dogs to 0, and the output at the end of each run will tell you whether the dogs went extinct. Running the model shows us that increasing the rate at which disperser groups meet above the baseline value, which is 1.0, will not really benefit population persistence, and that the frequency of extinction changes little when we increase the disperser meet rate from 1.0 to 2.0. However, reducing the ability of dispersers to meet will have strongly negative effects. As disperser meet rate is reduced from 1.0, the frequency of extinction increases dramatically. So in our journey through collectives, that is groups of individuals that strongly affect the fate and behavior of the individuals and the dynamics of the system, we have seen that we can model collectives either as results of emergent behavior or explicitly as a separate kind of entity with its own state variables and submodels. This explicit modeling requires assigning the properties and submodels of collectives to either non-spatial patches or to the breeds feature, or by using directed or undirected links. For this purpose, namely to model and analyze how the properties and behavior of collectives and individuals affect each other, as well as how the system affects both collectives and individuals, we need to build submodels for individuals and for collectives. Go ahead and stop the video here for a while and try out as many of these exercises as you can and then come back. And here is what you have learned in this module. Pause the video for a moment to read through these items and ensure that you're comfortable with everything on this list. In the next few slides, you will see the code for the entire meeting rate model. I'm not going to comment on this since you've already seen the piece parts and you've seen the explanations, but please do take the time and think through the entire model as it scrolls by.